record anyway, in case somebody wants to have a look later. I don't think that would be my choice. It's hard enough looking at it live, but I guess if it's recorded, you can put it on fast forward and go really quickly. Right? You don't have to listen to me as much. Okay, so here we are, sequences in chapter 11. It's section 1. A sequence is going to be a list of numbers, okay? And it differs from a set because the list of numbers is in order. So there's going to be a first element, then a second element, and so on. So you could call it an ordered set if you like. And we're going to be interested in infinite sequences as opposed to finite ones. A finite sequence just goes for a while and stops. Okay, and while those are interesting, and we can certainly model a lot of things in the world with the finite sequence, we're
sorry.
No worries. We're curious about sequences that are infinite, right? So they go on and on and on and on. And the most interesting thing about the sequence is what happens as it goes on and on. So we looked last time at several sequences and examples and saw some ways that we could represent them. You could write an explicit formula. You could write a recursive formula. You could just list several terms and put a dot, 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 and hope that your reader kind of recognizes your pattern. You could make a graph and so show a picture of the sequence. And of course, you can just describe the sequence in words. And it depends on the sequence itself and how you're trying to communicate on which of those representations is the easiest, right? If you're talking about the digits of pi, it might just be able to say, hey, this sequence R is the digits of pi, because those digits don't really have a nice explicit formula. Okay, but for other things, you might be, and most of the time when we consider sequences, we're going to give a regular explicit formula for the nth term, right? And so one of the things that you guys hopefully will do a little bit in the homework is change from one representation to another. And of course, the one that you are going to end up using is the one that is the easiest for you and helps you to get the most information about the problem you're trying to solve. Okay, so these now are all represented with explicit formulas. Back a while ago, when you first get introduced to sequences, we might say something like, list the first 5 terms of the sequence. So if I give you a formula, you give me a list. And we're going to just kind of cut to the chase and say, all right, where is this going? Because to be able to figure out where this is going, it's pretty nice to be able to list a few terms and have a look at them and see if you can figure it out. So we've come full circle, right? We are all the way back around to limit questions again. Where is this thing going, right? And for us, when we first started with limits, we said, what's the limit of a function as I get closer to a number, right? And we said, well, sometimes it gets all the way to that number and sometimes it doesn't, right? And here we're talking about the limit as n gets bigger and bigger. So an infinite limit, if you will. And we're going to say what's happening with the sequence. So if you remember when we did this a while ago, back in, I don't know, October maybe, we said the first step is simply to guess where it's going. Like guess, all right, where is this going? And see if you can provide some evidence that it's heading in that direction. Then the next step is to be a little bit more formal. If you're trying to really convince somebody it's heading there, and write an actual proof or come up with a mathematical argument that, you know, is more convincing that this is going where you say it's going. Okay, so the first thing is guess these limits, right? And provide some justification. And then when we get a little more formal, we're going to prove that the limit is what you say it is. So just exactly like we did way back in the very beginning. So to do that, I might take a look at these and just try a few numbers. So I'm going to stick some in, and I'm going to say, well, if I stick in 1, I get 1 over 2. And if I stick in 2, I get 2 over 3. So I get 1/2, right? And then I get 2/3, and then I get 3/4, and then I get 4/5. So the question is, you know, where's this going? 5, 6, ... right? Sometimes it's nice to look at the terms, and the terms will help you to figure out what it's getting closer to. So you might look at that and say, wow, that looks like the top, right, is going to be always a little bit smaller than the bottom. The bottom's going to be bigger than the top, so this is always going to be less than 1. But the difference between the top and the bottom, right, is getting smaller and smaller. So when we're way out here somewhere at, say, 99/100, you'd say, well, I don't know if I converted all those to decimal. It sure looks like that's getting closer and closer to 1. You'd say, I think that this limit is 1, right? Why? Based on this list, okay? And if you want to make a list or make a picture a little faster than just computing those all by hand, or if you want a more extensive list, you might go ahead and put it on Desmos. Right? You might go ahead and put it on Desmos and make a picture because, well, it's the same thing except Desmos is faster. So you would say A of n. We use A for sequences, right? It's a function with the set of natural numbers for the domain. Okay, and we're going to get n over n plus 1. Notice that Desmos thinks that you want a real valued function. So this is the graph of the real valued function n, or maybe x over x plus 1. But all we want is this value right here, that one right there, this one right here, because all we're going to do is plug in integers into our function. So to get the graph of the dots, we're going to make a list of numbers that we're going to stick in. For me, I use capital letters to represent the list so that I don't get confused about which is which. So maybe we'll go 1 to 100. And then what we're going to do is we're going to graph the dots n and a of n, a of n. Okay, and so here is the graph of our sequence. Okay? It's going up like this. So then you go way out here and you say, well, I don't know, it doesn't look like it's going up and up and up and up and up, although it's always increasing. It doesn't look like it's going up without bound. It looks like it's got some limiting value, and it looks to me like that's getting closer and closer to 1. Okay, so you could look at it in Desmos. That's another way that we could guess the limit. And then the question is, well, how do we prove the limit? And that's coming. That's what we're going to talk about today. Is that Shane? Good morning, Shane.
Good morning.
We're talking about sequences and trying to guess a few here in the warm-up, and then we're going to see if we can prove that it's going where we say it's going. Okay, so you might also try some kind of algebraic argument, because you already know if these were x's and we were talking about real values, then we already have a trick, right? It is change the function into another form that's easier to work with. And the question is, well, would that work for, you know, sequences as well? And the answer is yes. Okay. There are two things going on. One is, check this out back in Desmos again. And I'm going to write all these things down as some actual theorems. Okay. Notice how the green dots are following the red line. So our green dots are on the red line. In other words, this is the same function. So wherever this function for the real values goes, then this function has to go in the same place for the green dots. Right? The green dots don't get off of this red line. So wherever the red line is going, the green dots are going. This is kind of a nice observation, and we can formalize it a little bit more, but it basically says, if this function over the real numbers, if you can find its limit over the real numbers, then its limit over the natural numbers is the same. Okay, so we'd say, well, where would that go if this was just a regular old limit back from the good old days? And you say, I don't know, but I'm glad I'm not taking a year-long comprehensive exam. right? And you'd say, well, what about this? What if we said X, and I'll change to X. There's nothing, you know, really to be formal. We would have to say, you could say N is a real number, or you could say X is a natural number. But what we usually do is use X for reals and N for naturals. Seems to make sense. But unless somebody actually specifies, there's no official rule that X has to always be a real number. We just use it that way. All right, so how will we find this? You said, I don't know, maybe we'd use a trick. Do you remember the trick? Infinite limit, there's one big trick. I'll let you guys wake up. Divide by the highest power of the variable in the denominator. That's the trick. So this is to the first power. So divide top and bottom by X. And you'd get 1 over, right? 1 over X, oops, 1 plus 1 over X. You have to do it correctly. In other words, if I divide top and bottom by X, I get this new rearranged, written in a different form function. And then this one, we should be able to get using the limit laws. So the question would be, do the limit laws still work when I talk about natural domain versus all real numbers? And the answer is yes. And we're not going to go back and prove all of the limit laws again, but they do all work. And we'll see that. If you want to take a look at a little more detail, you can look in the book. So what is this saying? This is the limit of a quotient. That's the quotient of the limits. This is the limit of the sum. That's the sum of the limits. And we know where this goes. Where does this go when the bottom gets big?
Goes to 0.
That goes to 0. So 1 over 1 plus 0. Sounds to me like this goes to 1. And then you might make an argument that sounds something like this. The function for the real numbers goes to 1. So if the integers are following that same path, they have to go to 1 as well. Okay, and that's a pretty strong argument for the fact that this limit goes to 1. How are we doing so far? Okay, we're going to try to guess the limits and then come up with a strong argument for why we think it's going there, right? And the strongest argument we usually call a proof. So prove it, right? Prove that it's going where you say it's going. All right, so how about number 2? I kind of like that trick, but maybe you would investigate this one first because we're just starting to learn about this kind of thing. So you'd say, I don't know, Desmos seem pretty nice. So you pop this back up and you say, this time it's n over square root of 10 plus n. Okay, where's that going? I don't know. So far, it looks like it's just racing up there. Okay, if it just keeps going up, 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 then we'd say it just keeps going up, 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 up. But maybe we just have to get out further before it seems to level off. So the question is, does that look like it's leveling off, or does it look like it's going up forever? And you say, well, I don't know. It's hard to tell. That might be going up forever, but just really slowly. Okay, in which case, we would say it goes to infinity or diverges. Or it might be bending and leveling off. Yeah? Okay, so it's hard to tell. Remember back in the good old days, it was hard to tell, right? Sometimes looking at the graph isn't going to tell you the whole story, so you actually have to do the math to find out what it's doing. So maybe what we should do is look at the first few of these values. Yeah. Now we already got them graphed here, right? So you can say, well, what's that one? That's 0.302, that's 0.577. Clearly these are getting bigger, right? But the question is, are they kind of bending? Is it bending and leveling off? So maybe instead of going way out there and considering the graph, we do algebra instead. So we go back over here, and I like that trick that we just used. We say, maybe we consider the limit as x goes to infinity of x over the square root of 10 plus x. So now the question is, where's that going? Because certainly the integer values of our sequence are following, or the values of our sequence at the integers are following this real valued function. So how about same trick, divide top and bottom by x. So we'd say multiply by 1 over x and 1 over x, or divide top and bottom by 1 over x. Is that okay? You say, well, I don't know. Be bad if x were 0, wouldn't it? It's not 0, it's going to infinity. And it would be bad if it was actually equal to infinity, but it can't be equal to it. So what I'm thinking is, this is always defined. It's just getting smaller and smaller and smaller and smaller. Okay, so what do we end up with? We end up with the limit as x goes to infinity. We get 1 in the top. Now I got an x on the outside. So if I push it inside the square root, it's going to have to be squared. Okay, which, doing a little more algebra, whoops, x. I'm going to end up with something like 10 over x squared, right? And then over here, I'm going to have, did I just mess that up? Maybe I didn't. And then I'm going to have 1 over x. I think that looks right to me so far. So then I might ask, where is this going? And you'd say what?
0.
That's going to 0. This is going to 0. Square root 0 sounds to me like it would be 0. So I'm getting 1 over something that's going to 0. What does that sound like?
Does not exist.
Yeah, it does not exist. Right? It's getting bigger and bigger and bigger and bigger. So we would say this diverges. So even though it was bending, it wasn't flattening. It was just going up slower and slow. You know, it was still going up, but it was hard to tell in Desmos if it was going to flatten all the way out or if it was just going to continue growing really slowly. This one continues growing slowly, and so it diverges. Unless I made a mistake, I think that's right. I wrote some notes down somewhere, so maybe I better check. It seems like that's not what I anticipated, but I think it probably is right.
I checked on a calculator too, and the larger number you plug in, it just spits out a larger number. It doesn't get close to anything.
Right on. And that's another way you can do it. I think we did this before back in the day. We would say, hey, why don't I just try a of some, great big number? And in this case, it can get pretty big, right? What's it doing? It's just getting bigger and bigger and bigger and bigger. And so you'd say, well, I think it's getting bigger and bigger and bigger and bigger. And that's a pretty good argument for the fact that it does that. And then here we have sort of an algebraic argument for the same thing. So we'd say diverges. I don't know why we introduced this new language, but sequences we tend to say diverge and converge, whereas back when we did just limits before, we'd just say, doesn't exist, runs off to infinity. Basically, that's saying the same thing. All right, so then here's some more. So now the question is, how do we get these guys? And the answer is, I don't know, maybe we do something similar. Okay, so let's guess. The bottom, bigger than the top, yeah? So I'm kind of thinking the bottom's getting bigger faster than the top. But they're both going where? To infinity, yes?
Yeah.
So then the question is, does L'Hopital's rule still work? And what do you think the answer to that is?
Yeah.
Yes, L'Hopital's rule still works. However, maybe if you wanted to be certain, what you would say is, what if I were considering this function? Now L'Hopital's rule works for sure. Does L'Hopital's rule work for a sequence? The answer is, well, not really technically, because you have to take the derivative. The derivative doesn't exist at any point on this sequence. But if I consider this real valued function, then certainly these values are following this function. So wherever this function goes, this sequence goes. And so I can find this limit, and then I know that limit. And now, of course, you would use L'Hopital because this is infinity over infinity. Taking the derivative, we would get what, 1 over x, and down here we would get 1. And so as x gets really big in the denominator, this thing goes to 0, yeah, 0 over 1, 0. How are we doing on that one? Pretty good? Notice it's subtle. I use L'Hopital's rule, but I use L'Hopital's rule for the real valued function. And then I made the argument
My neck is definitely stiff from the rack.
is following
Oh,
the
yeah.
function. Boaz, I'm gonna quiet you down for a second. Are you there? There you go. Oh, yeah. Just turn it back on, and if you need to chat. Okay. So 3 more, and maybe we should just take a look at these. Take a look at number 4. That seems kind of curious. It's alternating. So this one's going up, down, up, down, up, down, up, down. Looks something like this. Minus 1 to the n. What happened here? Take a look at that one. What's that one doing? That one's going up and down and up and down and up and down and getting farther and farther apart. That doesn't look like it's converging to me. Okay, but maybe the one that we want does. Let's see if I can get it in here. Minus 1 to the n. Take a look at this one. This one's going up, down, up, down, up, down. Does that go getting closer to a number?
Nope.
No.
No, it's just bouncing back and forth. So you would say it's bouncing back and forth. This diverges. Notice that this is the first example of a sequence that diverges for a different reason than it runs off to infinity. So a limit might fail to exist because it goes off to infinity, goes off to negative infinity, or just simply bounces back and forth. Okay. We also have a situation where it could be going to one thing from one side and to something different from the other side, in which case we would still not have a limit. So all the limit rules that you learned still work. Notice if I divide by n now, now look at what's happening. It's bouncing back and forth still, it's alternating, but they're getting closer and closer and closer together. So I might be willing to say this does actually have a limit. What do you want to say it is?
0.
0.
0 or
Right?
1.
I'm going to say it's 0. Notice that this function still turned on, yeah? It's on. Where is it? This means for all real numbers, right? For all real numbers, where is this function? Because in the last couple of problems, what we did is we said, if my sequence follows my function and I know where my function's going, then I know where my sequence is going. Well, what's happening with this for all real numbers? Let's try a few. What if we put in some of these interesting real numbers that are in between our integers, like a half?
Oh, you need a square root
Yeah.
of a -1.
It's exactly right. That's the square root of -1, and that is not a real number.
You can't do that. Yeah.
So
and
you can't, wait, no, hold up. I don't want to mislead you. You can do it. You just can't do it on the real numbers. What kind of a number would it be?
it has to be a natural number.
Yeah, but I'm saying if I took the square root of -1, what would I get?
Oh, it's an imaginary number.
Yes, it is. So if we wanted to expand the numbers that we're talking about, we might say, hey, this function still has a limit over the complex numbers, but it doesn't have a limit for the real numbers. Okay, and then what we're doing in this section is we're saying, well, does it have a limit for the natural numbers? And so depending on the set of numbers we're working with, we might or might not get a limit. Now, I don't want to deal with complex numbers in this class because, well, we never have enough time. And now that we're working in this format and took 3 weeks off, you know, more or less, right? We kind of took 3 soft weeks. We really don't have time. But there's another class on complex numbers where we go and think about, well, what would happen if we looked at complex numbers? And I'm going to say graphing on a real number plane isn't going to help us because complex numbers don't live on this graph. So looking at the graph isn't going to help. Some of them do exist though, don't they? So if I took the cube root, it'd be okay.
Yeah.
But if I took the 4th root, it wouldn't be okay. So for most of the fractions, I would have a problem. Okay. And what if I did something even crazy, like I took an irrational number and I said, what's -1 to the pi power divided by pi? And well, it doesn't know. Okay.
Yeah. The reason is because when you're putting something to a power,
Mm-hmm.
and it's not exactly like a whole number, say it's like 3.5, right?
Right.
Well, if you remember that when you're multiplying 2 things with the same base that have exponents, you just add the exponents.
Okay.
Well, then technically with 3.5, something's got an exponent of 3, but then there's another thing with an exponent of 1/2.
Right
That's
on.
that's a square root. Doesn't exist.
That's
So
exactly right. Yeah, so I'm saying that the trick then that we used before, which said if I could figure out where my function's going, then I know where my sequence is going. Well, that works if we can figure it out, but we don't know where the function's going because the function isn't even defined for most of the values. And so that trick's not going to work on this one. That argument is not going to work on this one. But this argument works. Looks like it's getting smaller and smaller to me. Okay, it's just not a real strong argument because you have to say it looks like it. And what we might want is a stronger argument that says, well, I don't want to just know what it looks like. I want to know what it does. Okay, and so here's one thing that I might suggest. I might suggest that this function, I'm going to write it down here again. Okay, that the limit as n goes to infinity of -1 to the n over n is related to the limit as n goes to infinity of the absolute value of -1 to the n over n. I mean, what would happen if I took the absolute value of my function? What would it do to all my values in my sequence?
It would all be positive.
They'd all be positive. Notice that n is already positive. It's going to infinity. Okay, so what would happen here? It would be the absolute value of -1 raised to the nth power. And the absolute value of -1 is just 1. And 1 to the nth power is also just 1. So I'm kind of thinking that what we get is this. And what I'm wondering is, how is, and this limit we know, right? What is this going to?
0.
0.
That's going to 0. And here's a good argument for it. The function 1 over x goes to 0, and this is actually following that function. So this must also go to 0. Okay, now the question is, if I know where this one's going, can I say something about where the alternating one is going? And the answer is, yes, I think so. In fact, they're going to the same place. And maybe I can use Desmos to show you that. I'm going to fix my y-axis a little bit, since this is kind of starting and getting smaller. I'm going to go from -1 to 1. So I can spread it out a little bit so I can see it. Okay, so then let's take a look at this function. The function, I don't know, b of x, right? Which equals 1 over x. This half of the green dots is certainly following that curve. Would you agree? And then this half of the green dots, here, I'll do this. Is Desmos clever enough to get this? No. Okay, so let me write this, b of x. I'll come down here and I'll say c of x. Minus 1 over x. Okay, and these green dots are following this red curve. So half the dots are following this one, and half the dots are following this one, and we certainly know where the black one and the red one are going. Yeah, they're both going to where?
0.
0. So that means all the green dots must be going to 0 because this half of them are going to 0 and this half of them are going to 0. So they're all going to 0, which is a pretty good argument. The other thing that we could do is we could graph d of x is equal to the absolute value of a of x, yeah? We could just take all of the dots. Got to turn some things off so you can see them. Turn those off. Okay, where are my dots? Oh, I didn't graph them. Now I need to graph the dots. So the dots are now in D, yeah? That, now I'm confused about, oh, turn them on. Okay, there they are. They're green, right? They're green, but this is the graph of the absolute value. So when I took the absolute value, this dot that used to be down here got flipped up to the top, didn't it? So I made all of my dots positive. All the negative ones, when I took the absolute value, got flipped to the top. And now that all of the dots are on the top following the black curve curve's going to 0. The dots are following it, so they have to be going to 0. Now I think we got it. So the question is, did I prove it? And proof has to do with the audience. So if you believe me that it's going to 0, then I proved it. Okay. And if you're still skeptical and you want a stronger argument, then we have to think about it some more. Okay, well, we're going to do one more. No, we're going to do 2 more. And then we're going to look at some things formally. So now I want to look at the sine of pi over n as n goes to infinity. So what's this doing? And maybe the easiest thing would be to take a look at it. So we'll go back to sharing and we'll say, how about if instead of this now, I'm going to make this n. I'm going to say the sine of pi over n. And let's graph A. And let's get this other stuff out of here because it's getting kind of messy. So the question is, what's this doing, right? What's this doing? So it looks to me like it's doing what? Starts there, but then jumps up here, and then what? Looking like it's going to 0 or 1 to you? It's definitely coming down, isn't it?
Yeah.
Okay, so then the question is, how far down is it going? Maybe we would put in a big number and see. Looks to me like as the number gets bigger and bigger, it's getting closer and closer to 0. So once again, this isn't a proof, but it's pretty strong evidence that in fact this is going to 0. So here's the argument. Is this the same as the sine of the limit as n goes to infinity of pi over n? Meaning, oops, stop sharing. Meaning, if I know where the values that I'm plugging into the sine function are going, then can I figure out where these values are going and then take the sign? In other words, can I pull the sign outside the limit? And I think that that seems to make sense, right? The sign is a continuous function and it's acting on these dots. So if I know where these dots are going, then when I take the sign of each one of those dots, it ought to be, we ought to be able to figure out where that's heading. All right, so tell me this inside limit, what is it?
0.
0. So what's this going to? Sine of 0, which is 0.
Yeah, this I think this makes sense because if you think about it, the limit of the function should be what the value of the function at the limit.
That's exactly right. That's exactly right. And to be really formal, we would want to prove that that's true. And under what conditions is that true? One of the conditions is going to be that our function needs to be a continuous function. And I think we did something similar to that way back when we were proving the limit laws. I think it's actually limit law, I don't know, like 8 or 9 or something like that. And if you want to be really formal and take an advanced calculus class somewhere down the road, then you're going to spend a little bit of time proving those kinds of statements that you just made. Okay, and then looking at conditions for when are those statements true and when are they not true. But according to the graph in Desmos, sure looks like it's true for the sine function. Okay, and now let's see, we got what, one more? All right, I like this one too. This is the limit as n goes to infinity of n factorial over n to the n. So do you remember what factorial means?
Isn't it times by like if it was like 10 factorial, it's like 1 times 2 or whatever, where it's
Yeah.
like number.
Yes, times, like this.
Yes.
That's it. It means multiply all the numbers from 1 to 10. But what kind of numbers?
It's just the natural numbers, right?
Just the natural numbers from 1 up to 10. So then it begs the question, you know, what's this? And the answer is, so far it's what? Nothing. It's undefined. We don't know what that is. How do I do a half factorial? You can't multiply together all the integers from 1 up to a half. And so I can't do it up to 9.5 either. So this we might define somewhere else later down the road. But for now, that doesn't make any sense. So what was our trick? Our trick that we've been using is, well, what if we considered, where is this function going? Then we could say these follow those and these go in the same place. But now I got a problem with this. What's the problem? It's kind of the same as the one that we did before with the root, right? Can I plug in all real numbers to the top? And the answer is no. The only numbers I can plug into the top are the natural numbers. And so this function's undefined for most of the real numbers. Just like we had a problem with the square root of the negative on the alternating series. So this argument's not going to work. So we're going to need a better argument. So one of the things that we might do to get started, which is what I pretty much always do on all of these, is have a look at it. You know, what is it doing? We got n factorial over n to the nth. And you say, gosh, looks what? Like it starts out pretty good. You might need to know what 1 factorial is. It means 1. 1 to the 1 is 1. So it starts out at 1, and then it does what? Looks like it's going down, and it looks like it's going down to 0 to me. So I would probably guess that 0 is a pretty good answer, wouldn't you? Okay, why is this undefined? Desmos ran out of decimals because 10 to the 10th power is already getting pretty big. And 100th to the 100th power, that's getting really, really big, isn't it? Okay, so how do we prove it? Can't do it this way. That didn't work. So how about divide by the highest power of the variable in the denominator? Well, that works good. This is the nth power. So I would get n to the nth. Divide by that, I get 1 in the bottom. But then I'd get n factorial over n to the nth in the top, which is what I started with. That trick didn't work. This is definitely going to infinity, and this is going to infinity. So maybe you say, well, I'm going to use L'Hopital's rule and take the derivative. Why would that be a problem?
What's the derivative of something to the factorial?
I don't have, that doesn't even have a derivative. That's not a continuous function, right? In fact, it's exactly a discontinuous function. It's only individual dots, no derivative. And furthermore, L'Hopital's rule only works, right, if we're talking about this function down here that's continuous for all real numbers. So that doesn't work, no derivatives. So now we're really stuck and we need a new argument. So let me give you this one. And I'm gonna write this out like this. This equals the limit as n goes to infinity of 1 times 2 times 3 times 4 times 5 times ... times n, yeah? Just gonna write out factorial about what it looks like. And n to the n means n times n times n times n times n times ... times n. I think I'm getting this. This one's equal to what? N over n? For n not 0? That's 1.
Isn't it just 1?
Yeah, it's 1. But what about this one, and this one, and this one, and this one, and this one? Those are all fractions, aren't they? N is bigger than all those things. So this is a fraction. This is a fraction of 1. And this is a fraction of a fraction of 1. And this is a fraction of a fraction of a fraction of 1. So what are you kind of thinking this might be?
Oh, 0.
Where does this go? That goes to 0, doesn't it? Where does this go? That goes to 0. This one goes to where? 1. 0 times 0 times 0 times 0 times 0 times 1? Sounds to me like it's going to be 0. And so that's the best argument that I can come up with for why I think this goes to 0 so far. Okay, our goal here is for you to take a sequence and for you to consider, first of all, to represent that sequence in a lot of different ways. So you want to write it as a recursive rule, as an explicit rule, as a list, as a graph, and move back and forth between those different representations. The next thing that we want to do is we want to say, all right, well, where's this sequence going? And the first part of figuring that out is just literally guessing and then starting to build an argument for why we should believe you. Some of the evidence might be a graph. Some of the evidence might be a list of numbers that seem to be getting closer to something. Some of the evidence might be some algebra, right? Some algebra that you did. Some of the evidence might be that you argue that this list is following this function. And then you can use what we know before to prove where this function's going. Some of the argument might be that if I take the absolute value, then all it really did is flip the values up to the top, and then I can see where those values are going. Or you might say, for alternating ones, I'm going to consider the set of all the positive ones and where they're going, and then the set of all the negative ones and figure out where they're going. And if they go to the same place, then it all must be going there. Some of the argument might be that if I do a limit of a function of a sequence, that I should get the same thing as the function of the limit of the sequence. Because if the sequence is going there, and I take a function of those values, that's got to be going to wherever the function of the limit is. I don't know if I said that right. I actually think Shane said it better. Okay, you might use the definition and say, well, what does n factorial mean, or n to the n mean? And write it out the long way, and then see if you can see where that's going. So here are some arguments. But what if none of that works? Or what if you really want to be a little bit more formal? Then we have to get more formal. So let me get a tiny bit more formal, and then we'll see if we can wrap this up. Okay, a sequence. Math types like things to be really nailed down. So we would say a sequence, and we would call it a sub n. So sometimes when we're talking about sequences, we'll put them in those little parentheses. And so with, without, I don't know, people would probably understand you either way. We say it has a limit, right? L. And we write that the limit as n goes to infinity of a sub n is equal to L. Okay? Or sometimes we write a sub n goes to L as n goes to infinity. Right? Sometimes you'll see it written this way. Okay, if, okay, if what? You're going to love this part. It's going to sound familiar. If for every small number, say epsilon greater than 0, okay, there exists, okay, some number in the natural numbers. I'm going to call it big N. It's an element of the natural numbers. Sometimes, sometimes right here, you'll see of the positive integers, because the positive integers and the natural numbers are the same. Yeah. Okay. Then, wait a minute, such that what? The distance between the value in the sequence and the limit is less than epsilon, provided our number is bigger than this number that we picked n. In other words, we do an epsilon delta proof, except in this case, we don't have a delta. We just have some big number. So we sometimes call it an epsilon n proof, if you like. And it says this. Check this out. I'll draw a picture. Here was our sequence. 1/2, 2/3, 3/4, 5 of whatever that one is, 6/7. Yeah. What's it doing? It's getting closer and closer to 1. Are you remembering this? This was our example. So what does our rule say? If I want to prove it, then what do I have to prove? For every small number, right? For every small number epsilon, I want to consider how much error is there? How far away from the limit am I? So how far away am I right here? You say, this is 1/2, yeah? The limit was 1. So how far away am I? Everybody go to sleep. 1 minus 1/2.
1/2.
Half. Yeah? Okay. And then I say, how far away am I right here? This was 2/3, right? So now how far away am I?
2/3.
Close.
Third.
A third.
1/3, yeah, 1/3. And now how far away am I here?
A fourth.
1/4. And now how far away am I right here?
Fifth.
1/5. This says that for every little distance, so you pick some nice distance. Okay, I pick epsilon, nice epsilon. Epsilon is 1/10. Okay, I pick epsilon as a 10th. And then you have to tell me what? There has to be some number. There has to be some number such that the distance away is less than a 10th for the rest of the sequence. For all numbers bigger than that. So how far away would I be at 1/10? In fact, which value is the 10th? This is the 10th value, right?
It's the ninth.
Oh, 1/10, right? That would be the 9th one, wouldn't it? So at the 9th one, we get 9/10. And of course, that 9/10 is right there, right? And then this distance would be 1/10. So at 9, I'm 1/10 away from the limit. But now if I go over another one, like to 10, then I'm where? 10/11ths. And so I'm only 1/11th away now. So basically, you have to find n such that, right, such that for all the rest of the values of my sequence, right, I have to be closer than 1/10. Is that making sense? Okay, but it has to work for all of them, doesn't it? So if I give you 1/10, you say choose what? Choose n equals 10. Because from 10 on, I'm going to be closer than 1/10. And if I say epsilon is 1/100th, you'd say what? Choose n equals
101.
101. 101 would certainly work. If you wanted to cut it off right exactly, I think n equals 100 would work. But any n bigger than 100 would certainly work. So that's how the game plays. Do you remember how we did this before? We said, I pick an epsilon, you find a delta that works. And we played this game for a while. And then we said, well, it has to work for any epsilon. And so I pick an epsilon, you give me a rule for finding the delta. And if you can come up with that rule that works for all the epsilons, then you did the proof. And the same is going here. I pick an epsilon, you have to give me an n that works. But if I pick any epsilon at all, then you have to give me a n that works. So check this out. Let's see the rule. So what's the rule? If I pick epsilon is 1/100th, then you say, maybe I should say this backwards. We used different language before. Maybe I should say, let epsilon be 1/100. Then we would say, choose, right, our n to be equal to 1/epsilon. Wouldn't that do it? Which would be 100 in this case. All the values bigger than 100 would work. And so for any tolerance, I can give you an n where the rest of the sequence is close enough. Then I proved it. We're not going to do too many formal proofs with epsilon delta style. We didn't do a lot of those back in the limit days when we first learned these because they're messy and they're hard. But I think there are some homework problems for you to explore this a little bit. We're going to use some higher level arguments, if you will, the kind that we were using earlier today when we were looking at the limits. And what I'd like to do is I kind of like to formalize those a little bit. And so there's going to be a bunch of theorems that are all listed sort of in the book, and I want to get them sort of down on paper, at least a few of them, so that we can kind of formalize the ideas that we were doing before. The ultimate go-to for actually proving that the limit exists is to write an epsilon delta proof, right? Is to write and use the definition to write a proof. You got to find this rule. But it turns out that that's hard, just like it was way back in chapter 3. And so what we do is we try to develop some higher level tools that we can use that are easier than writing an epsilon delta proof. Okay. And again, if epsilon delta proof is your thing, you can take advanced calculus and spend like a month just writing epsilon delta proofs till you get really good at it. Okay, so if that sounds like fun, well, sounds better than having coronavirus, but other than that, I don't know. You guys will have to decide. I had a couple of students bail and one went and played the flute instead, you know, and so I don't know. Me personally, I'm not very good. You know, I'd struggled with piano, so I imagine flute would have been hard. But you can find your path, right? We're not going to spend a lot of time with epsilon delta, but I wanted you to see the definition for sure. Okay, so here are some of these rules that we've been using today. Here's a nice one. I don't know what theorem number this is. Of course, the book is, Stuart's going to number all these. You can put numbers with them if you want. If the limit as x goes to infinity of f of x equals L. Notice that because I'm using x's, I'm not going to explicitly state that x is a real number and f of x is a continuous function of a real number. Okay, that's kind of goes, that it's kind of be implied because I used the x. But of course, if you wanted to write this out formally, like in a book with all the details, you'd have to say where f is a real valued function. Yeah. Now, how would you prove this limit? The same way we did back in chapter 3. Okay, and f of n equals an for n in, they like to use the positive integers here. Okay, I usually say the natural numbers, but they use the positive integers a lot, I guess, or whatever book I wrote this was looking at when I kind of wrote these notes. They use the positive integers. So you'll see sometimes natural numbers, sometimes positive integers, same. So what does this say? This is saying I got a function and I know where it's going. And the values of my sequence are following right along the function. Because if I take f of the integer values, I'm going to get a value that's on this function. Well, that means the sequence is following the function. So what do you think we can say?
Then the limit of the function would equal the limit of the sequence.
Right on. Then the sequence has to go to the same place. So it's a theorem, right? We would have to actually prove this. So how would you prove it? You'd have to use an epsilon delta proof to prove that this is a true statement. So we would have to consider all real valued functions f, and we would have to say, what happens if they're following along? Can I show that there's an n such that beyond this n, I'm always close enough? I'm going to skip the proof. Not because we couldn't consider it, and not because you guys aren't smart enough to consider it, but because I want to kind of look at some other things, okay? If we go off and try to do all these proofs, then it's going to take us the rest of the time and maybe more than that. Okay, and there's a whole class for doing just this. So I'm going to save this proof for later, for another class. Okay, just simply because we can't look at everything at the same time. All right? Not because you guys couldn't do it. We could certainly go do it right now and you're smart enough and you can handle it. Okay, but we got to save something for later. So I'm going to save the proof of this for later. And one of the reasons I'm saving it is because I think this is pretty obvious. If the values in my sequence are following my function and I know where my function's going, then I know where my sequence is going. I mean, that seems pretty intuitive. We good?
Yep.
Okay, There's another definition that I think I'll let you look up in the book, and it says this: if you can't find that n, then what do you think we say the function or the sequence does? Remember our definition of a limit? What happens if the limit doesn't exist? Then we say that the sequence what?
Diverges.
Diverges. So when we're listing this all out formally in the book, there's a definition for diverge. And basically diverge says there is no limit. Okay, so if there's no limit, it diverges. If there is a limit, it converges. And we say it converges to the limit. So next thing that we might say, all the limit laws work. So limit laws work for sequences. Okay, now oh no. Now we're gonna have to prove this, right? But I have a feeling that this theorem is gonna be pretty helpful for proving that the limit laws work for sequences. Because if you wanna prove, let's just do an example. If I wanna know where the limit, or that the limit of a sub n plus b sub n goes, then what do I want to probably say? I want to say that's the limit, right, as n goes to infinity of a sub n plus the limit as n goes to infinity of b sub n. In other words, if I have the limit of the sum, it's the sum of the limits. That's a limit law, isn't it? So how would I prove this is true? I might say that if I can show that there's a function, then the limit law works for functions. So if I know that this sequence follows a function and this sequence follows a function, then I can use the limit law for functions, right, of real values to prove the limit law for sequences. That would take care of a bunch of sequences. But we already saw some sequences where we don't know what the function's going to. We can't take square roots of negative numbers. Okay, we can't take logs of negative numbers. We can't do n factorial with fractional powers. So this isn't, so we've got a little bit more work to do here. Okay, but I think it makes sense. It says if one sequence is going somewhere and the other sequence is going somewhere, then if I add them together, they have to be going to the same place. And I think that seems fairly intuitive. Again, when we did this back in chapter 3, we proved this statement writing an epsilon delta proof. And we would have to do the same thing, okay, here. All right, but I'm just going to take that on faith because, again, I think that feels pretty intuitive. Next one, theorem. Here's the theorem. If the limit as n goes to infinity of the absolute value of a sequence equals 0, then the limit as n goes to infinity of the sequence itself must be what?
0.
0. Notice that this isn't quite as general. It gets you some of the absolute values, right? It gets you some of the sequences that alternate. If the alternating one is going to 0, then we can say that the sequence is going to 0. We already saw an example of that. But if the if this is going to a number not 0, right? Let's say that when I take the absolute value, it's going to 5. Well, if it's going to 5, then I don't know what the sequence is going to. This turns out to be really weird, and we should maybe look at an example, but maybe I'll save it for Monday. Okay, or you might come across it in the homework. This sequence has to be going to 0. Let me go back and see if I can show you that one again in Desmos. We had an alternating sequence. What if I put a, oh, get over there. What if I put a -1 to the n in front of this? Now what's it do? Check it out. Up, down, up, down, up, down, up, down, up, down. Yeah? Where's it going? 0.
Zero.
Yeah, that makes sense, doesn't it? It's alternating and going to 0. Okay, what if we have one that's alternating, right, but not going to 0? You say, well, wait a minute. What if I took the absolute value of this, right? If I take the absolute value of this, what do I get? I get 1 to the n. You want me to put it on here so you can see it? We'll say b sub n, right, is equal to the absolute value of a sub n. Okay, and then so where's that thing going, right? Where's b sub n going? I don't know, maybe we should graph it. N and then b sub n. That's not b. And then b sub n. You're saying, well, it sure looks like it's going to 1 to me. Yeah? In other words, the limit of the absolute value is going to where? Purple's going to where?
1.
1.
1. It's 1 all the time. It's always 1. It's going to 1. It's going to be at 1. In fact, how much error is there? 0, right? So for every n, we're within 0, right? We're exactly right on the limit. But even though the limit of the absolute value goes to 1, look at where the sequence is going. Up, down, up, down, up, down, up, down, up, down, up, down. Yeah? In other words, if the limit of the absolute value of the sequence is going somewhere other than 0, like say to 1, we don't know if this is going to 0 or not. It might just be oscillating back and forth. But if the limit of the absolute value does go to 0, then we know that the sequence has to go to 0 as well.
Well, I mean, if there is a horizontal asymptote at 0, the function has to exist at the original at 0.
Yes. No, not necessarily. It doesn't have to exist at 0. It just has to be getting closer and closer to 0.
Oh yeah, the limit. It can't,
Okay.
basically it can't pass that, is what it's saying.
Yeah. So this one's special though, right? Because it's got to be around 0. Otherwise, it might just be bouncing back and forth and you don't know if it's getting closer to something. So that's kind of a funny one. I'll let you try some problems with that and you'll kind of see what I mean. And then we have what I call a whole bunch of limit problems. We already did a bunch of those. So that's awesome because we already did the rest of these notes. So let me see where I am with you. This section has a lot of definitions to get us started. So it's kind of long. All right, we did all those examples. We did all these examples. This is beautiful. I might ask you this now, and we might write it as a theorem. For what values we might say of R, does this sequence R to the n converge? So now what we're saying is, instead of just saying, I give you a specific R and I ask you, does it converge or diverge? Now I might ask you, can you find all the values of R for which it converges or diverges? Here, take a look at this sequence. The limit as n goes to infinity of R to the nth power. So what about if R is 0? What do you think about that? Converge or diverge?
R is 0.
Yeah, if R equals 0, we'll make a list. R, 0. Right? Where does the limit of the sequence go?
Yeah.
I'll just write L. What do you think? Goes to what?
0.
0, yeah, because what are all the values? 0 to the first, 0 to the second, 0 to the third. They're all 0, 0, 0, 0, 0, 0. What's the limit?
0.
0, yeah? Okay, that looks good. What if R is 1?
R is 1.
Yeah, R is 1. So the limit is
1.
1. Yeah, because what's 1 to the 1, 1 to the 2, 1 to the 3? They're all 1s, aren't they? You doing good so far? Let's try some more. What if R is a half? That means I would get the limit is n goes to infinity of 1/2 to the nth power, which is the same, isn't it, as the limit as n goes to infinity of 1/2 to the n?
Yeah. So then,
That'd be 0 as well, right?
That looks to me like it's going to be 0. Yeah? So I'm thinking it's definitely going to converge for 1/2. The bottom's getting bigger, 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 right? The top's staying 1. So if they're dividing by something big, it's going to 0. So we found 3 values of r for which it converges. Do you know any values of r that it probably diverges?
2.
Try 2, right? So that would be the limit as n goes to infinity of 2 to the n. Well, what's 2 to the n doing? It's
Bigger, bigger, bigger.
2, 4, 8, 16, 32. Sounds to me like it what? Goes to infinity. And we would say diverges. So 2 doesn't work, right? 2, so 2 doesn't work. So what could you put in here? Sometimes, like we did back from limits in the good old days, we said it goes to infinity, right? And we use it as a noun, even though we probably shouldn't. Right? We say the limit is infinity, although we should really say it's just getting bigger and bigger and bigger. It doesn't exist. So you found some that worked. You found one that didn't work. What about all the rest of the values? For what values of r does this work, and for which values of r does it not work? Right? That would be my question. And I'm going to leave that for you to think about. And then we might have a rule. In fact, I might even call this like a power rule or something, because it's a number raised to a power. So for what powers does it work, and for what powers does it not work? And we might be able to come up with some rules. Rules are nice, because if you ever see another limit that you have to prove, and it's one that looks like this one, then you already know the answer. Right? So I'll leave that for you to think about. What else do I have? What else do I have? Do I have anything else I want to talk about today? No, I want to talk about this on Monday. I think that's enough. I think that's enough. Yeah, and then I've just got a whole bunch of problems to work out. So maybe it would be good for you to pause here, because we just did a whole bunch of stuff, and then for you to practice on a few on your own. So what you're going to find in the homework is a bunch of sequences, and it's going to say, where are they going? And then you're going to come up with an argument for where you think they're heading, okay, using some of the theorems and some of the ideas that we talked about today. I wouldn't be surprised if sort of toward the end, you start to run into some that maybe we can't get using the ideas that we've talked about so far. And maybe we need to come up with some more tools. And so we'll add a few more tools to our toolbox on Monday as we kind of wrap up this section and kind of get the ones that you aren't able to get. So as you guys are practicing these, if there's some you're stuck on, well, you're always welcome to come and ask me a question or send me an email, or you could just make a note and you can hold on to them until Monday, and then we can work them out together. Sound okay? Is that enough for this week? Well, congratulations, you guys. You're doing a really good job. This is difficult circumstances at best, right? But I really am hoping that we can send you on to Calc 3 and wherever else you're going, ready, right? As much as you can be, given this situation. I suspect that a lot of people are just going to go, it was a crisis. I just gave everybody their midterm grades and passed them and sent them on, which is fine if you don't ever need to use this stuff, I guess, right? You're like, woohoo, I didn't really want to write another paper in English, but for us, I think you guys really need to, I'm thinking this is part of your pathway, and actually knowing this stuff is going to be pretty helpful as you go down the road. And so hang in there, learn as much as you can. And I suspect, given your effort and your, tenacity here of being able to hang in here and get as much done as you can, that it's going to give you an advantage, maybe over, some other people who just decided they wanted to take an extra, month off. And unfortunately for those that, had to take a month off, right, because of job and family and maybe even being sick themselves. So, just be thankful that you can study math. Right? I guess that's kind of a crazy thing to say, but keep it up as best you can. So have a great weekend, right? Stay safe, and I will see you guys on Monday.
Thanks. See you Monday.
Okay.
Thank you.
See you Monday.
Mm.